what is the cosmic microwave background radiation, and why does it have a temperature? The cosmic microwave background radiation is residual radiation, that is, it is electromagnetic radiation left over from the Big Bang, which has been physically stretched to microwave wavelengths, due to the expansion of cosmological spacetime. It has a temperature because all forms of electromagnetic radiation can be expressed in terms of its black-body radiation temperature. And that's why the cosmic microwave background radiation is expressed in terms of temperature. So, does this mean that space-time has a temperature? Yes, absolutely it does. But how so? Because the cosmic microwave background radiation and the space-time it transits cannot be separated into cosmic microwave background radiation and nothingness. Hence, space-time has a temperature. The cosmic microwave background radiation is the most precise measurement of any cosmological attribute known to science, and shall remain so for many years. Buried within the cosmic microwave background radiation is a plethora of information which may be utilized to describe the history of the cosmos, from the Big Bang to the present epoch. However, in this episode, we will utilize the principles of space-time engineering we have developed over numerous episodes, to derive the cosmic microwave background radiation temperature from the cosmological Hubble constant derived in the previous episode. In other words, we'll show you how to derive the cosmic microwave background radiation temperature from particle physics. So, let's get started. The first step in deriving the cosmic microwave background radiation in terms of the Hubble constant, is to derive the Hubble constant. Fortunately, we have already achieved this objective in episodes 9 and 10. In episode 9, we derived the Hubble constant at the instant of the Big Bang, and in episode 10, we derived the Hubble constant for the present epoch. In fact, we derived two Hubble constants in episode 10, that is, the cosmic distance ladder measurement, as well as the cosmic microwave background radiation power spectrum measurement. We have termed these as being the astronomical Hubble constant, and the cosmological Hubble constant, respectively. It should also be emphasized that the results we obtained in episode 10, are nothing short of astonishing. The correlation of our results to experimental observation are almost miraculous, as evidenced by the experimental value published by the Particle Data Group, appearing on screen. In this episode, we will focus exclusively on the power spectrum value of the Hubble constant because it is already associated with the cosmic microwave background radiation. For the sake of brevity, and to save time, we encourage viewers to review episodes 9 and 10, as we shall not be repeating their derivations herein. So, having said this, let's move on. The second task we face is to establish a relationship between the space-time being created at the instant of the Big Bang, and the cosmic microwave background radiation transiting through it. To achieve this, we shall consider the maximum permissible mass density condition, as appears in episode 9. From this, we extract the mass term. This represents the minimum fraction of mass associated with the singularity at the center of a Schwarzschild black hole of cosmological mass, as appears in episode 10. In other words, this mass fraction denotes the minimum permissible mass of any Schwarzschild black hole. Notably, this is not an assumed value, this is the value calculated in episode 9. Please refer to episode 9 and 10 for more information. Whilst keeping in mind the minimum mass fraction as defined on screen, we will now introduce some standard physics. From this, we can extract the equivalent population of photons within the minimum mass fraction. Hence, utilizing the definition of a graviton from episode 6, the equivalent graviton population is trivially determined, expressed in terms of photon frequency and mass. Let's recall that the maximum permissible mass density condition of a Schwarzschild black hole of cosmological mass was derived in episode 9. This is theorized to represent the condition of the universe, momentarily prior to the Big Bang. As a consequence of utilizing this maximum condition, even at its minimum mass fraction, the quantum vacuum cutoff frequency is constant for all quantities of mass, so long as the maximum mass density condition is preserved. Therefore, we may simply plug in the value we calculated in episode 9. Once we have substituted all values into the graviton population equation, the value returned is 8 on 3. This is a measure of the mass energy being absorbed by the quantum vacuum, per minimum mass fraction, per period. Let's now turn our attention to what's happening with the Hubble constant. We calculated the Hubble constant at the instant of the Big Bang in episode 9, and already calculated the value of the cosmic microwave background radiation power spectrum Hubble constant in 2020. Moreover, the cosmic microwave background radiation power spectrum Hubble constant was exhaustively derived in episode 10. We saw in episode 10 that the electrogravity-magnetic flux density decayed logarithmically, so we'll execute a similar process here. In addition to this, we'll recognize that the ratio, 8:3, is also a proportional measure of the rate at which space-time is being created. By this we mean, a proportional measure of the rate at which the quantum vacuum is absorbing gravitons. Therefore, when we relate the rate of space-time creation with the logarithmic decay of cosmological expansion, we arrive at the final relationship for this slide, and we'll utilize it on the next slide to derive the cosmic microwave background radiation temperature. The last thing we need to do in order to complete the derivation of the cosmic microwave background radiation temperature is establish the thermal expansion function. This is a very simple activity and should pose no conceptual difficulty. We commence by utilizing the wavelength associated with the second simplified harmonic cutoff frequency, as presented in episode 10. If we evaluate the wavelength at the Schwarzschild radius for a black hole of cosmological mass, that is, at the Hubble length, we obtain the thermal expansion function as shown. Once this has been completed, the solution for the present epoch cosmic microwave background radiation temperature may be trivially formulated, and subsequently evaluated, as shown. Once again, the electrogravity-magnetic construct has produced an astonishing result, and once again, we must emphasize that our methodology should not be dismissed. Let's now generate a general solution which our viewers may easily utilize. The process to do so doesn't really require any explanation, it's just a simple matter of substitution. However, what is important are the results generated, as shown. We can see that the particle data group Hubble constant contains an error because it does not produce the experimentally measured value of cosmic microwave background radiation temperature. This means that the particle data group 2022 Hubble constant is not cosmic microwave background radiation constrained, and in fact, is in conflict with their own temperature measurement. It should be quite obvious to viewers of all the episodes so far, that we may utilize our present epoch cosmic microwave background radiation temperature solution, to also constrain the virial galactic mass of the Milky Way, to the cosmic microwave background as well. This is what we're going to do on the next slide. In episode 10, we derived an expression for the cosmic microwave background radiation power spectrum Hubble constant, which we term as being the cosmological Hubble constant. By injecting this solution into the present epoch cosmic microwave background radiation temperature equation, derived on the previous slide, we may crystallize a new configuration in terms of the solar distance to the galactic center, and galactic virial mass. As you can see, a commonly cited total Milky Way mass value of m sub double g, produces an invalid result for cosmic microwave background radiation temperature. However, the cosmic microwave background radiation constrained value of galactic virial mass produces the experimentally validated result, exactly. So, what does this mean, and how can the widely cited result be incorrect? Well, to answer these questions, we first need to appreciate the meaning of virial mass. Virial mass refers to the amount of mass within the Milky Way, which is gravitationally bound together. This means that the associated virial radius is a non-physical point in space, rotating about the galactic center. Hence, our m sub g value of Milky Way virial mass denotes the gravitationally bound mass in the Milky Way, which exists in thermal equilibrium with the cosmic microwave background. However, the m sub double g value is not in thermal equilibrium with the cosmic microwave background. This may not mean that the m sub double g value is incorrect, it may mean that it is correct, but satisfies some other form of equilibrium. In other words, m sub double g may be the correct answer to a different problem. Milky Way virial mass is the topic of a later episode, so for now, we'll move on to the summary. The journey through this episode has been considerably less arduous than the preceding episode. The most difficult task was already completed in episode 10, that is, deriving the cosmic microwave background radiation power spectrum Hubble constant. Hence, the derivation of the cosmic microwave background radiation temperature was quite easy. Notably, once again, the electrogravimagnetic construct has produced astonishing results, based fundamentally upon the principle of zero-point field equilibrium, that is, all matter exists in equilibrium with the ground state of the quantum vacuum. From this foundation, we have achieved three key outcomes. Number 1, we have derived the cosmic microwave background radiation temperature in terms of the power spectrum Hubble constant. Number 2, we have constrained the power spectrum Hubble constant, and the Milky Way virial mass, to the cosmic microwave background radiation temperature. And number 3, all of our solutions and cosmic microwave background radiation constraints are derived from particle physics. For viewers wishing to consult literature relevant to this episode, you may do so by accessing the links shown.